All right, moving on from polynomials to rational expressions. In this appendix, we reduce, multiply, divide, add, and subtract, and simplify rational expressions. So rational expressions are really just quotients of polynomials. In fact, that's the formal definition of a rational expression. And now we've got some experience with polynomials and factoring polynomials. What we'll do with the rational expressions is simplify them, and that was something we didn't do with the polynomials. So formally, a rational expression is a quotient of polynomials. The polynomial in the role of the dividend is called the numerator. It's the one on top in the fraction. And the polynomial in the role of the divisor is the denominator. It's the one on the bottom of the fraction. When the numerator and denominator of a rational expression have no common factors, well, except for plus or minus 1, the rational expression is said to be reduced to lowest terms or simplified. And you've probably got experience in simplifying rational expressions from your past. A little warning, again. When simplifying rational expressions, we have to be careful about domains of expressions. This is all based on the fact that you can't divide by 0. You can't divide by 0 in precalculus. Though it might look like it sometimes, you can't divide by 0 in calculus either. You take an upper level class, you won't divide by 0. You go to graduate school, you do math research, you don't divide by 0. Nobody divides by 0. So that's one reason for making a big deal out of this. Another is very subtle things that happen in calculus. In calculus 1, when you deal with limits, which is the first topic covered in calculus 1, you're never dividing by 0 because that doesn't make sense. But you have expressions that if you're not careful, division by 0 will arise. So you better be careful. So what we'll do in this section is simplify rational expressions with this eye towards we can't divide by 0. When we simplify, we cancel terms and possibly lose information. Well, you can't lose this information for reasons related to division by 0. And we'll illustrate this with a whole bunch of examples, as always. Some properties of rational expressions include A divided by B times C divided by D is simply the product of the numerators divided by the product of the denominators. Oh, if we don't divide by 0. Get used to looking at this. We're going to say this a bunch. Really with an eye towards calculus, mostly. A divided by B divided by C divided by D, the quotient of A and B divided by the quotient of C and D, is A over B times D over C. What we've done in dividing by this quotient, C divided by D, is invert and multiply. Those words probably sound familiar to you. So we've taken C divided by D in the denominator and written it as D divided by C, inverted it, and changed it from the denominator into multiplication. So division by a quotient is equivalent to multiplying by the reciprocal, invert and multiply. And we know how to multiply from part 1. You take the product of the numerators and the product of the denominators, provided none of those denominators are 0. Get used to that again. A over B plus or minus C over B. So these have the same denominator, in which case you simply add or subtract the corresponding numerators, provided that denominator is not 0. If we look at a sum or difference of two quotients that don't have a common denominator, we got to find a common denominator, and that'll be some of the manipulations of this appendix as well. A divided by B plus or minus C divided by D, we need a common denominator. A common denominator is B times D. So let's take A over B and multiply it by D over D. We're multiplying by D in the numerator and denominator. These will cancel to undo this. We don't want to undo it. We want to get a B times D in the denominator of the first one. We want to get a B times D in the denominator of the second one. We already got the D, so we need to insert the B. So we'll multiply by b in the numerator and the denominator, none of these parameters being 0. And that'll produce a denominator of BD in the second one and a denominator of BD in the first one. In the process, the numerators get modified. So this produces AD divided by BD plus or minus BC divided by BD. Both of them are divided by BD. Falls back to this case. They now have a common denominator of BD. So we add or subtract their numerators. That would be AD plus or minus BC in the numerator with the common denominator. Can't emphasize how important this is in terms of getting common denominators before adding things together. So dealing with quotients, multiplication's easy. You don't need a common denominator. Division is just another kind of multiplication. There really is no such operation as division. It deals with multiplication of inverses. There's also no such operation as subtraction. It really is dealing with additive inverses and addition. So, strictly speaking, division and subtraction are not real math operations. Now, we're going to continue to deal with them. But strictly speaking, they deal with inverse operations as related to addition and multiplication. The two operations are addition and multiplication. You add negative numbers and you multiply by reciprocals, if you like, to get the corresponding subtraction and division ideas. But the multiplication and division are easier with quotients than is addition and subtraction. With addition and subtraction, you have to get a common denominator. So that makes that potentially more involved. Let's do some examples. All right. Little technical difficulties there. Let's see if I can't get this to work properly. There we go. Okay, here's a quotient, 4x squared plus 8x divided by 12x plus 24, if you like, a rational expression. So it's a quotient of two polynomials. We want to reduce it to lowest terms, simplify it. So we factor the numerator and denominator and cancel what we can, with that warning about not losing information and division by 0. 4x squared plus 8x. Anything in common? A 4 is common to both, and an x is common to both. So let's factor 4x out. That'll leave us with x plus 2, right? Let's distribute and check that. 4x times x is 4x squared. 4x times 2 is 8x, right? 12x and 24, we can factor 12 out, and that's all. So we'll get 12 times x plus 2. Hey, and there's a common expression that can be canceled if we're sufficiently careful. This expression is equivalent not to this expression. Let's talk about that briefly. If I consider what's written here and what's written here and ignore this, this is false. This has a domain of definition of all x's except for -2. X cannot be -2 because that gives division by 0 in this expression, in this rational expression. By the way, you get a 0 in the numerator as well, but nobody cares. You can't plug in -2 because it gives a 0 in the denominator. That's the problem. So this is undefined at -2. This alone is defined at -2. You plug in x equals -2 in this, you get -8 over 12. But you can't plug -2 into this because you have division by 0. So this expression and this expression, 4x over 12, those are not equivalent expressions. They don't even have equivalent domains of definition. And the whole problem is -2. So we got to explicitly write out that this equals this if x is not -2. So The expressions themselves are not equal. They're equal everywhere except at -2. So you got to write that down. It seems like a subtlety. It isn't. This idea is what makes a bunch of calculus tick. So when you do limits and derivatives in Calculus 1, lots of it is based on this idea of cancellation, but with concern over the fact that you've modified the function. Either that or you explicitly write out, well, I'm not letting you use -2 in this expression. If that's the situation, then 4x over 12, where x is not -2, that does equal this expression. You've lost information. In this expression, you can't have x equals -2. In this expression, you can. That's why you have to write, we take this second expression under the conditions that x is not -2. Get used to it. That's how you simplify correctly. Let's see, there's a factor of 4 in the numerator and denominator. 4 goes into 12 3 times. So we could write this as 4 times 3 and then cancel the 4s. No issues there. It's the variables. When we cancel expressions with variables in them, that I have to put these disclaimers in. So that original expression equals x over 3 if x does not equal -2. It doesn't equal x over 3. It equals x over 3 provided x is not -2. So this is the complete answer in the box here, not just x over 3. You work one of these on the test and you don't put the disclaimer on there. It isn't right. It's close. I'd go with partial credit, but it's not, strictly speaking, it's not completely correct. You don't put this in, it's wrong. Let's do another one. With an eye on this, cancel things, lose information. Don't forget the conditions that have to be stated in writing. Okay, a second one. This time, we're multiplying two rational functions and then simplifying. Perform the indicated operation, multiplication, and simplify the result. Leave your answer in a factored form. A quick little font comment. Notice it's a bit difficult to see on the slides, but this is an X is in times, whereas this X font looks ever so subtly different. I was using a different font. For example, in the class notes, it uses different fonts, and the X's don't look anything like the time symbols. But be very careful. They look a lot alike. They are subtly different. I mean, this one has a slight tilt to it for one thing, and this one's very square. But this is read 3 over 2x times the time symbol, x squared over 6x plus 10. All right. Perform the multiplication and simplify. All right. Multiplying quotients, it's a piece of cake. You just multiply the numerators and the denominators. So we get 3 times x squared, 3x squared, and 2x times 6x plus 10, producing this. So the multiplication operation was easy. We'll do one with addition next, and it'll be a little more complicated. Now, can we cancel some stuff? Are there things common to the numerator and denominator? Can we simplify? Yeah. There's an x that's common to the numerator and denominator. Here's where we left off in the computation. So we can take one of these x's and cancel it with this x. Cancel the x, and that produces this. Oh, provided x is not 0. It's the same type of situation we had on the previous slide. If I don't write this down, these are not equivalent. This you can't plug 0 into because you get division by 0 because of that. This you can plug 0 in if I don't write this down, in which case you get 0 over 20. 0 over 20 equals 0. This equals 0 when x equals 0. This is undefined when x equals 0. That's why you have to write if x doesn't equal 0. Whenever you cancel like this, using variables, you have to make sure you haven't lost information. This contains the information that x can't be 0 because there's an x in the denominator that would make the denominator 0. This alone doesn't contain that information. So you got to write it in by hand to make them equivalent statements. Okay, anything else we can simplify here? We could factor a 2 out of this. There's a 2 common to 6x plus 10. Factor that 2 out, that would produce a 4 here, and you'd be left with what, 3x plus 5? Factoring 2 out, yeah, that's right. So the original expression simplifies down to this, with part of the answer being x not equal to 0. We get this expression, provided x is not equal to 0. Let's do another one, but this time, this time we're dealing with compound fractions. All right, perform the indicated operation and simplify the result and do the factoring like we just did. Okay, well, multiplication won't be too bad. Dividing by a quotient is equivalent to multiplication by its reciprocal, invert and multiply. Maybe is the verbiage you use. So we can take this rational expression divided by that rational expression, rewrite the numerator, take the denominator, invert it, take its reciprocal, and multiply. Division is multiplication by reciprocals, which is why division isn't a real operation algebraically. So anyhow, we take the reciprocal and multiply. Multiplication, easy with fractions. Multiply the numerators, we get 8x times x plus 1. Multiply the denominators, we get x squared minus 1 times 10x. Okay, so we've performed the indicated operation, which, and I'll continue to treat division as an operation, even though it isn't. We've performed the division operation to produce this. Now we need to simplify. Is there common stuff? There's a 2 there and a 2 there. It's one thing we can cancel. Hey, x squared minus 1, that's a difference of 2 squares, x and 1. So we have from, I think it was section A1, we stated something like x squared minus a squared is x minus a times x plus a. We've got that with a equals 1. We got a difference of 2 perfect squares, it's also called. But x squared minus 1 factors is given here. So we can take this in the denominator and rewrite it as x minus 1 times x plus 1. So the original expression equals this expression. Ooh, there's an x plus 1. We can cancel if we're careful. Next slide. Just recopied what we had on the previous slide. We left off here. Okay. We can cancel the x plus 1s here. We can cancel the x's here as well. Canceling the x and the x plus 1 terms. We can cancel this and this, but we'll lose information. You can cancel the x's provided x is not 0. You can cancel the x plus 1s provided x is not -1. When you cancel these two things, you're going to produce something of this form. You're just going to have an x minus 1 in the denominator. We've also canceled the 2 to get to here. So we've canceled a factor of 2 from the 8 and the 10. That's where the 4 and the 5 come from. We've canceled these, and we've canceled the x's. So the only thing with x's in it left is this x minus 1 right here. But the original expression doesn't equal this alone. It's the same problem. Look at this up here. Can x be -1? Of course not. You have an x plus 1 in the denominator here. Can x be -1 here? Just this part? Yeah. Plug in -1, you get 4 divided by 5 times -2. You get what? -4/10? No problem for x equals -1 there. But that's not the same behavior as this, or equivalently of this. X can't be 1 here. I'm sorry, x can't be -1 in this, so x can't be -1 in this if we get the equality. And for similar reasons, we have to write out x can't be 0. It's because we cancel the x's. Certainly x can't be 0 in this because of that. X can't be -1 because of that. And you don't see that information here, which is why you have to write it explicitly. Hey, x can't be 1 here, so we can't have x equals 1 in the stuff in the box. X can't be 1 because that would give division by 0. Is that information preserved down here? It is. X can't be 1 is implied by this because, well, we got an x minus 1 in the denominator still. So I don't have to write x can't be positive 1. That's implied by the existence of this in the denominator. Up here, x can't be 1. It's implied. X can't be negative 1. It's implied by this. X can't be 0. It's implied by this. Down here, the x can't be one thing is implied, but the other two things aren't. That's why you have to write them out by hand. So I will be quite picky about this because this is a way to do it correctly. And this is such a fundamental concept when you move into the Calculus 1 material. Let's see, let's go back to the notes. Yeah, returning to the notes. When adding rational numbers, fractions, we must get a common denominator and do so usually by finding the least common multiple of the two denominators. The least common denominator, it's more commonly called. They're going to use this least common multiple verbiage, but it's the least common multiple of the denominators. So we're going to do the same thing with rational expressions. So here comes a mouthful of words. We'll illustrate what it really means. All we're doing in the following is the same way you add fractions back in, I don't know, 6th grade when you first started adding fractions, but they were numbers then. Well, it's the same idea now, except there'll be x's all over the place. And we'll follow the same concept of finding a least common denominator, a least common multiple of the two denominators. The LCM method for adding or subtracting rational expressions requires 4 steps. Factor completely the polynomials in the denominator of each rational expression. Factor the denominators. The least common multiple of the denominators is the product of each of these factors raised to a power equal to the greatest power of the factor in the denominator of the rational expression. We'll illustrate that with an example, but the punchline is you consider all factors and you take the biggest power of each factor. Rewrite each rational expression using the least common multiple as the denominator. So here, this is where you're producing the common denominator. Add the numerators of the rewritten rational expressions, which now have the least common multiple as the common denominator. So you're factoring, you're finding a least common denominator and forcing that on the fractions and then adding them. Fractions, rational expressions. Let's look at 2 examples of that. Okay. Perform the indicated operation, it's subtraction this time, and simplify the result, leaving your answer in factored form. All right, first step was factor the denominators. No problem there. It's x minus 3, linear term, already factored. Maybe this factors. In fact, it does. Notice x squared plus 5x minus 24 factors as x minus 3 times x plus a. Okay, we described this in section A3, where we found the little a and little b integers, where we wanted the product of a and b in this case to be negative 24, and we wanted the sum of a and b to be 5. What are pairs of numbers that multiply, integers, that multiply to give negative 24? 1 and 24, or one of them is negative. 2 and 12, or one of them is negative. 3 and 8, where one of them is negative. And I think that's it. We start repeating after that. 4 and 6 is another one. 4 and 6, where one of them is negative. So anyhow, we need to go through that list of things and find a pair of numbers which add to give positive 5. In that list, negative 3 and positive 8 are the ones that work. Negative 3 times 8 is negative 24, and negative 3 plus 8 is positive 5. So since this has so many divisors, this one is a little more lengthy to go through and determine the parameters that yield a factorization, but this is it. I leave it to you to convince yourself that the little A and B process produces exactly this. So we can factor the denominator in this second expression, rewrite the given terms by factoring that denominator as indicated, x minus 3 over x plus 8. Now, that was step one in the LCM method. Now we want to get a common denominator. This has a factor of x minus 3, so does this. So we'll need an x minus 3 in the denominator of both. This has a factor of x plus 8, so this is going to need one too. So we need to get an x plus 8 in the denominator of this first rational expression. We'll do so by multiplying by x plus 8 over x plus 8. That's just 1, isn't it? Unless x equals negative 8. That information is hidden in this quotient up here, by the way. But we'll multiply by x plus 8 over x plus 8. That'll produce an x plus 8 in the denominator of the first expression. There it is. And it introduces an x plus 8 in the numerator. But you had to do this to get the common denominator. You do the same thing with numbers. So by multiplying by x plus 8 over x plus 8, this first rational expression that produces this, we found the common denominator, the least common multiple LCM of the denominators of what was given up here. So same denominator, now we can do the subtraction. Now that we have a common denominator, now we can do the subtraction, producing x times x plus 8 minus x plus 1 over the common denominator. Let's deal with the arithmetic here and further simplify. Distribute, x times x is x squared, x times 8 is 8x, minus x minus 1, distributing the negative, produces this. That's x squared plus 7x minus 1. Here's the denominator. That's a second degree polynomial. Can you factor it? Doesn't factor over the integers. Let's discuss that briefly. I'd look for a and b that multiply to give -1 and add to give 7. Well, the only integers that multiply to give -1 are 1 and -1. And they don't add to give 7, they add to give 0. So this can't be factored over the integers. If you go through the A-B stuff, I'll just state it authoritatively, but that's the reason why that's can't be factored over the integers. And so this must be the simplified version. We've got it as factored as we can. We canceled any common terms. Actually, there wasn't anything to cancel this time, but we've got it as factored as we can, and we perform that operation. The operation is complicated because it's addition or subtraction, and it involves rational expressions. Addition and subtraction with rational expressions, that's the thing that takes up time because you have to find a common denominator. Let's do another one with a more complicated denominator situation. Same instructions, do the subtraction and simplify. The denominator for the first expression is x plus 2 squared times x minus 1. The denominator for the second expression is x plus 2 times x minus 1 squared. So this has 2 factors of x plus 2 and 1 factor of x minus 1. And this one has 1 factor of x plus 2 and 2 factors of x minus 1. So this needs another factor of x minus 1, and this needs another factor of x plus 2. We need both of them squared to get the common denominator. That's what was described in that LCM method, the greatest factor idea. The greatest factor related to x plus 2 is x plus 2 squared. The greatest in terms of x minus 1 is the square term. We need a square on both of them to get the common denominator. So we'll do the same thing we did in the last example, except this time we got to do it to both rational expressions. We need another x minus 1 in the first one. We'll multiply by x minus 1 over x minus 1. That'll give us an x minus 1 squared in the denominator, and some stuff happens in the numerator. We need another x plus 2 in this one. We'll multiply by x plus 2 over x plus 2. That'll give us the denominator we desire, and some stuff happens in the numerator. Performing the multiplication, common denominator, x plus 2 squared, x minus 1 squared on the first one and the second one. It worked. The stuff that happens in the numerators, we pick up an x minus 1 here. We pick up an x plus 2 here. We can combine those because now we have the common denominator. So there's the subtraction part being performed. And now we'll simplify. Multiply out, distribute. We get 2x minus 2 minus 6x minus 12 as given here. That's 2x minus 6x leaves us with a negative 4x. Negative 2 minus 12 produces a negative 14. We can cancel a 2 or factor 2 out of this, a negative 2. So factor a negative 2 out of this gives us negative 2 times x plus 7. And there you go. It's in simplified form. There's nothing left to factor because we've got entirely first degree polynomials, x plus something, and nothing cancels. There's nothing common to the numerator and denominator to cancel. Back to the notes. When a quotient has sums or differences of rational expressions in the numerator and or denominator, the quotient's called a mixed quotient. Compound fraction is a more common term, at least with numbers. To simplify, a mixed quotient means to rewrite it as a rational expression reduced to lowest terms. So we're going to have fractions inside fractions and go through and deal with that. Actually, we dealt with one earlier. They give us a protocol by which to deal with it, and we'll illustrate these two methods. To simplify a mixed quotient or compound fraction, treat the numerator and denominator of the mixed quotient separately and simplify each. If the denominator of the mixed expression is itself a rational expression, then invert the denominator and multiply. Invert and multiply. So this says simplify numerator and denominator separately and then invert and multiply. The second one, actually probably the easier one, says find the least common multiple of the denominator of all rational expressions, the numerator and denominator. Multiply the numerator and denominator of the mixed quotient by the least common multiple, divided by itself, and simplify the resulting rational expression. All right, again, a bunch of words. The technique is not as complicated as it sounds. But let's look at two examples. Let's do method 2 and method 1. Let's actually do the second one first because it's actually the easier one. So perform the indicated operations, which is some addition, some subtraction, and some division, and simplify the result. Leave your answer in factored form. Okay. That second method said find a common denominator, least common multiple of the denominators for all rational expressions. This has an x squared, this has an x squared, this is, I don't know, 4 over 1 and 3 over 1. But x squared is the least common multiple of all the denominators under discussion. The least common multiple in both the numerator and denominator expressions is x squared. So we're going to multiply by x squared over x squared. It gets rid of the compound fraction. So we could do a more complicated one, but this should illustrate the idea. You get rid of the compound fractions. So we'll take the original expression, multiply by x squared over x squared. You can't argue with the validity of that. X can't be 0. Right, there's an x in the denominator right there that tells us x can't be 0. So that information carries on. I don't have to write nothing about if x doesn't equal unless I cancel some stuff. So we must cancel some stuff before we get to this point. So we'll multiply by x squared over x squared. Distributing, that'll give us 4x squared plus x squared over x squared. Down here in the denominator, we get 3x squared minus x squared over x squared. Don't just cancel. When you cancel, you have to make disclaimers. So simply distributing produces this. Do you know I desperately want to cancel those x squares there and there? and write those as ones. And you can do that if x is not 0. We've lost the information by losing the x's in the denominators, going from this step to this step. So you have to add this disclaimer. This is valid provided x is not 0. Can you plug 0 into this if you ignore that? Without that there, yeah, I can plug 0 into this. I get out 1 over -1. Both of these will become 0. Well, if that equals this, then you ought to be able to plug 0 into this. You can't plug 0 into this because you get division by 0. That's why you have to put the disclaimer in. Again, got to put the disclaimer in whenever you cancel expressions involving x's. You have to explicitly write out the x's that made those expressions yield division by 0. Those x's are disallowed. In this case, it's simply x equals 0 itself. Can't happen. So this and all of this are the same. Can you simplify this? You can't. This is a perfect square plus a perfect square. This is 2x squared, and this is 1 squared. That's prime. We stated, I think in Appendix A1, this is prime. This can't be factored over the rationals. It can't be factored over the irrationals, but we're not worried about that. Take your A-B process. I need two things that multiply. Oh no, I got a 3 out front. I'd have to factor the 3 out and explore it in more depth. This can't be factored over the rationals. Can be factored over the irrationals, it turns out. You do some square roots of 3 or square roots of 1/3 type things. There's a way to factor this. Not our concern. When we've described simplified, it's always been with an idea towards integers. So we'll leave this as the answer, even though this could be further factored, but not using integers. More on the factoring with the irrational numbers, and I think it's in the last few sections of the appendices. So the original expression is equal to all of this. If you leave the if x doesn't equal 0 part off, it's wrong. It's very subtly wrong, but wrong is wrong. I give partial credit for that, but there's a deep concept going on here with this idea about the excluding x equals 0. These two functions, forget this, they're not the same. They're the same everywhere except at x equals 0. That's why you got to write this in on the right-hand side. Another one. Okay, so this is a bit more involved. We'll use that method 1, least common multiple. What we're going to do, same instructions, is we're going to do the subtraction in the numerator by finding a common denominator. Then we're going to do the subtraction in the denominator by finding a common denominator. And then we're going to invert and multiply. Either that or find the least common multiple of all these denominators, x, x minus 3, x minus 3, and x plus 3, and multiply numerator and denominator by that. That would eliminate the compound fraction right there. So for the sake of illustration, let's do it by performing this arithmetic first and this arithmetic first, and then dealing with a compound fraction. Okay, so in the numerator, you want to add these two fractions together. What's the common denominator? Simply the product of x and x minus 3. This needs an x minus 3 in the denominator. This needs an x in the denominator. We'll multiply the first one by x minus 3 over x minus 3. That'll give us the x minus 3 in the denominator. We'll multiply the second one by x over x. That'll give us the x in the denominator. And some stuff happens in the numerator. Now looking at the denominator of the compound fraction. X minus 3 and x plus 3. Least common multiple of those two is their product. This needs a factor of x plus 3 in the denominator. This needs a factor of x minus 3 in the denominator to get that least common multiple of the denominators. So we'll multiply the first one by x plus 3 over x plus 3. We'll multiply the second one by x minus 3 over x minus 3. Performing the multiplication yields this. So we've got 2x plus 5 times x minus 3. There it is. Over x times x minus 3. There it is. X squared, well, x times x over x minus 3 times x. x times x over x minus 3 times x. In the denominator, similar thing. X squared, x plus 3, x squared, x plus 3, x plus 1 squared times x minus 3. There that is. Notice in the numerator, denominators are the same, common denominator here. And in the denominator, we've also got common denominators. There's a bunch of denominators because it's a compound fraction. But now we can do the subtraction. So we can do subtraction here. It's done with a common denominator. We can do the subtraction here. It's done with a common denominator. Then we can invert and multiply. Next slide. Okay, we've inverted and multiplied. So let me go back and look at that. Here's a numerator. We're going to take this, multiply by its reciprocal. So we'll have this times the reciprocal of that. The x minus 3, x plus 3 will appear on the top in the numerator. Invert and multiply. So next slide, we'll see this times the reciprocal of this. This times the reciprocal of the old denominator. So inverting and multiplying, as we're told to do in one of the previous notes, produces this. Now we're multiplying fractions. So should be downhill from here. The hard stuff is adding and subtracting fractions, and we've done that part. Multiply. Okay. That's easy enough. I just take this numerator times that numerator, this denominator times that denominator, but we need to simplify as well. So we're going to have to multiply some stuff out in addition. But the multiplication is straightforward. Let's FOIL this. Let's expand that. I want to simplify this expression. 2x plus 5 times x minus 3. FOIL it. Let me not spend an inordinate amount of time on this. We've got first, outer, inner, last. It produces these numbers. Trust me, these notes have been pretty thoroughly proofread. From that, we'll subtract the x squared. By the way, upon doing that, we'll have 2x squared minus x squared is x squared. Negative 6x plus 5x, negative x. There's a negative 15. So this numerator expands and simplifies to this. Let's see, here's some arithmetic, some addition or subtraction. Let's deal with this as well. Let's expand all this stuff out. We'll distribute the x squared over the x plus 3, producing an x cubed plus 3x. Ooh, we'll have to square this. Okay, x plus 1, that'll be the first one squared plus the last one squared plus twice the product. When you square a binomial, first squared, last squared, twice the product. Product is 1x, twice that. That takes care of the squaring. Bring the x minus 3 down. All right, so we've multiplied here to produce this. We've multiplied this out and distributed here to produce the denominator on this one. So more arithmetic needs to be done. Let's see, from here to here, we simplified the numerator. We looked at that. Let's deal with the rest of this. Now we got to deal with this product. We'll distribute the x onto each of these and then distribute the negative 3. Distributing the x will produce an x cubed plus 2x squared plus x cubed plus 2x squared plus x. Distribute the negative 3 will produce a negative 3x squared minus 6x minus 3. So the distribution's been done. There's still a negative sign out front. Now simplify this. Okay, let's see. We got an x cubed minus x cubes. The x cubes are gone. How about squares? Here's a negative 2x squared plus 3x squared. Don't forget to distribute for a net 1x squared, positive 1x squared. For the x terms, here's a 3x minus x plus 6x. 3x minus x would put us at 2x plus 6x would leave us at 8x. That's right. In the constant term, there's only one constant term. It's negative 3. It's positive 3. So all that arithmetic produces this. We can write the original expression as this divided by that times this divided by that. Anything we can cancel? Yeah, we can cancel those x minus 3's. So let's cancel those x minus 3's, but that's cancellation with a variable. Don't forget to write after that cancellation that you're no longer allowed to use x equals 3. So we get the thing with a 15 in it here, the x plus 3 is here, the x is here, the thing with the 8 in it is here, and the x minus 3's were canceled, and we justified that cancellation as given here. Can you further factor these two things? You cannot. You go to town with your little a and little b ideas of a times b equals negative 15 and a plus b equals negative 1. You won't find anything. This is irreducible. This can't be factored. And a similar technique shows this can't be factored either. So the original expression simplifies down to this. In the original expression, here it is, you couldn't have x equals 3. See, you get division by 0 there if you had x equals 3, so you can't have x equals 3. Do you see within this the fact that x can't be 3? You do not. You can plug x equals 3 into this expression, all else being equal, and you get some number out. But if this is supposed to equal the original expression and x can't be 3 in the original expression, we better disallow x being 3 in this. That's, again, why you have to tack on the expression x doesn't equal 3. Extremely fundamentally important stuff, this idea about disallowing certain x values. It's one of the first things you'll do in Calculus 1 when you explore something called limits. You'll deal with this concept of disallowing certain values. We've got functions that are equal everywhere except at a certain value. And then that value becomes of supreme interest when you're dealing with a thing called limits in calculus. For pre-calculus, that takes care of illustrating those two methods of manipulating rational expressions. That takes care of the rational expressions stuff. And in the next section, Appendix A6, we'll look at algebraic manipulations. I forget the precise title of it, but the first 6 sections of the appendices are super essential to the material in this pre-calculus class, with the exception of one on synthetic division, which we'll skip. There's a couple of sections at the end of the appendices that are also important, and I'll make sure you got videos for those as well. So have a nice day. I'll see you in section A.6 next time. Catch you later.